Good night, everyone, and welcome back to your channel. Let's review a PE structural sample question. So we have like a cantilever beam and handling a spandrel loading. So it's a second degree loading, and also the beam is 1 degree indeterminate. So as you can see here, we have like W a second degree loading start at B and just increases goes all the way to the fixed end and reaches to W there. We want to calculate the reaction at B. So this is a professional engineering structural sample question, but I strongly believe that a senior bachelor student can also easily solve this problem with a few insights. So let's jump to the solution. So if we dissect our problem into two determinate beams, so if we just remove the reaction at the support at B, we just convert our problem into our indeterminate problem into two determinate beams. So the first one handling the original loading, and the other one, it'll replace the force of this reaction and call it RB, R sub B, or reaction at B, and then calculate the deflection for these two beams. So that's RB plus we can call it delta 1 for the first beam plus delta 2 for the second beam, and we know that delta at B is equal to 0 because in the original beam we have a reaction at B, we have a support at B, so there is no up and down movement there. And our condition is delta 1 plus delta B is equal to delta 1 plus delta 2 is equal to delta B, and we do know there is no downward movement for B because there is a reaction at B, so delta B is equal to 0. So if we just move to the calculation of delta 2, because that's pretty easy and any engineering student uh, know that that's RBL cubed over 3EI, or you can just move to the references to get easily find the delta for a single load on a cantilever beam, either upward or downward. Mhm. And then now let's jump to calculation of the delta 1 for our cantilever beam with a, a spandrel loading or second degree loading. So for example, if you want to calculate RB, let's start it a bit simpler here. So if we have a cantilever beam handling a distributed loading of W with the length of L, we definitely know that our reaction is simply Fr, or resultant force is simply WL. If we have the same beam, but this time with a triangular loading, we do know that our resultant force this time is Fr is equal to a half of WL because our area just goes half. And then if we have the same beam, which is our case, but this time we have like a second degree loading, all intensities are W. And then this time our Fr, or resultant force, is, just remember it's 1/3 of WL, and we will see later on that why a resultant force for a second degree loading is equal to 1/3 of WL. But with this intuition, you can just go, this is the WL, this is a half of that, and this is 1/3 of that. We'll move to the logic for this later on. So if we just draw our shear equation, it just goes up with RA, which is equal to resultant force, and that's WL over third. Just accept it for now, and we'll move to this one. And then draw the M over EI. And then let's just jump to the centroid calculation, the logic for that 1/3 WL. So this is the centroid calculation. If we call it X bar for a, consider we have like a general spandrel with the length of B and height of H. We want to calculate X bar or centroid from the base of our spandrel. So it's the equation for general spandrel is a coefficient like y is equal to k times x to the power of n, and then n could be 1 2 3 4, not 1 2 3 4, like any number higher than 1. So x bar is b, or the length, over n plus 2, and area is b times h over n plus 1. That's the general equation. Again, you can find it in the references or any structural or mechanic of solid textbook. So let's just go it for a parabolic spandrel, which is, that's another term for the second degree loading. So that's y is equal to kx squared, and in such case x bar from the base of our spandrel is b over n plus 2. So x bar is b over 4, and our area is definitely bh over n plus 1. So area for second degree loading, that's bh over 3. Do you remember we call that if we have like a second degree loading and we want to calculate resultant force? That was exactly our case. We have like just the location of a spandrel is just vice versa. Fr is just the area under loading, isn't it? So that's, if this is L, this is W, Fr is 1/3 of WL. It just replace B and H with our case. That's 1/3 of 1/3 of WL. That's the logic for our case. So remember this calculation. And for a cubic or third degree spandrel, that's the, just go with the formula. X bar is b over n plus 2, replace n by a 3, which is the cubic spandrel, and definitely x bar or centroid from the base of a spandrel is b over 5, and area is a b times h over 4. So our case again, our equation is a second degree or 1/3 of, or it just says our FR is 1/3 of WL. There's no reaction, only RA. So when you draw the shear diagram, it just comes up to WL over 3. And then if the loading is second degree, definitely the shear diagram is third degree. And the area under shear, it just goes like, if this is the third degree, area is BH over N plus 1. And don't confuse, replace BH by W, my bad, L and W, WL plus. So if our N is 3, we are going to calculate this area under shear, which is going to be the initial amount for our M over EI diagram. So if N is 3, the area is 1/4 of WL over 3 times L, and this is the exact, and if multiplied by 1 over EI, it is the exact amount for the initial amount for the M over EI or Y prime diagram. And with the same logic, we just go on, and then this is the fourth degree equation. So following the same pattern, FR, the loading is second degree, shear is third degree, and definitely the moment is fourth degree. So definitely again, X bar from the base is a n plus L over n plus 2. So n is 4 here, so x bar from the base is L over 6. Definitely the other distance is, we call it x1 prime, that's 5 over 6 times the length of the original beam. So x bar is L over 6 and area is again BH. B is L and H is W. So with the second the second the moment area theorem, delta at B is equal to tangential deviation of B with respect to a tangential deviation of B is equal to delta at B is tangential deviation. My bad. It's just, let me draw it correctly. So it just says a delta at B, delta at B is equal to tangential deviation at B with respect to a vertical line. This is vertical line which passes through A. So this is the second moment area theorem, and that simply says M, the area under M over EI times x1 bar is equal to delta 2 or delta at B for our second case. So if we go with the same logic, that's the area 1 over 1/5 of WL squared over 12 EI. So this is fourth degree. Area is 1 over 5 WL, 1 over BH, let's say. And definitely 1/5 is here. Our H this time is WL squared over 12 EI, and our uh, B is definitely the length times x bar 1, which is 5 over 6 times L. And if you do the math, it simply gives you WL to the fourth over 72 EI. And if you have that, now calculation of RB is simply the superposition of delta 1 plus delta 2 and add them up together. And because the delta at B is equal to 0, it simply says delta B is equal to 0. So the summation of delta 1 plus delta 2 definitely should be 0. So WL delta 1 plus delta 2 is equal to 0, and it simply says the only unknown in this problem, which was the calculation of RB, reaction at B, was uh, is simply calculated to be WRB is equal to WL cubed over 24 EI. Thank you. We'll solve more interesting problem in next videos.